So now let's look at how to prove the quadratic formula. So again, we have this equation here. ax squared plus bx plus c equals to 0, and a is now 0. So first we divide each term by a. So the left-hand side becomes to this, right? All the terms are divided by a. And then we subtract c over a on each side, and we add this term on each side. So this becomes, so on both sides, we add this term, and then we subtract the c over a on the left-hand side, and then we subtract the c over a to the right-hand side, right? So this is equal to say we move the c over a to the right-hand side. So there's a minus c over a here. And then we can combine the three terms into a term here, the square term here. So how we come from this to this is that we use a formula, a general formula called n plus m squared equals to n squared plus 2nm plus n squared, right? So here in this example, m is x, and m is b over 2a, right? So this becomes x squared plus 2 times x plus 2a, and b, and plus n squared is b over 2a squared, right? So this is just the three terms here, right? So we use a general formula, the general formula here, to combine the three terms into one large term here. And then we take the square root on both sides. So first, the left-hand side becomes x plus b over 2a, and the right-hand side becomes the square root of this thing, right? But pay attention that we have a plus or a minus sign here because we take the square root, right? And so if we take the square on both sides, then we can find that this term, after we take the square of both sides, so this is just this equation here. But when we take a square root, there's a plus or minus sign here because both the positive or minus term, after they take the square, they have the same result. So that's why after we take the square root, we have the two roots here, two solutions here. One is positive, one is negative. It's simply because when we take the square, we have the same answer, but after we take the square root, we should have the positive one and negative one. Okay. And then after we arrange, we find this. And then we move the b over 2a to the right, so we find our solution here. So x equal to this thing, right? So we have the two roots here, and we end our proof here. So back to our problem, p squared plus 4p minus 5 equals to 0. So in this example, a equals to 1, b is 4, c is minus 5. Right, and all we need to do is to plug in the three numbers to the general formula here and to find the two roots. So here the two roots are p1 star and p2 star. So this is 2a, and the minus 4 here, it should be minus b, and then after the square root, it should be 4b squared minus 4ac, right? And so this is 2 as minus 4 plus 6 over 2, or minus 6 minus 6 over 2, right? So this is 1 and this is minus 5. So here we have two distinct roots. One is 1, one is minus 5. So here we find a solution to this equation, but it's not our problem because our problem requires that the roots represent the price. right? So the price cannot be negative, and so we exclude the -5 root here. So only one that's left that fits the problem is 1. So the equilibrium price should be 1. And for the equilibrium quantity, the Q star here, you can plug in the P star, right? Plug in P star to any of the equation QD or QS. And then you can find that the Q star is 3. Okay. So next, we talk about higher degree polynomial equations. Before that, we talk about linear equation and quadratic equation. So the degree of x, the highest degree of x is 2, right? But what if the degree of x is beyond the 2, right? So for example, in this equation, x cubed minus x squared minus 4x plus 4 equals to 0. So here we have x cubed here, right? It's higher than x squared, right? So here we have, this is called a higher degree polynomial equations if the highest degree of x is larger or equal to 3. So it's not easy to find a solution or find the roots to this equation, right? One simple way that we can do this is to factor the function, right? Factorization, we call this factorization. But in most of cases, it's not that easy to factor the function, but this is a relatively simple and easy function that we can do this. So I see by factorization means, first we can see that the first two terms, if we combine these two terms, we can find that this equals to x squared times x minus 1, right? We just plug out the x squared term, and what's left is x minus 1, right? Because x squared is a common term in both x cubed and x squared here, right? So we plug out the common term and combine the rest of them. And for the last two terms, we can also do the same. The common term here is 4, right? Both of them can be divided by 4. So we plug out 4, and what's left is again x minus 1, right? So we combine the 4 little terms into 2 terms here. And then we find that, okay, both of these large terms have one common divisor. It's called x minus 1, right? Both of them have x minus 1. So again, we can plug out x minus 1, and then what's left, we combine them together. So what's left is x squared minus 4, right? And if we still want to factor the function, we can still factor the x squared minus 4 into these two terms, the multiplication of these two terms, x plus 2 and x minus 2. So here we use a general formula to do this. The a squared minus b squared equals to a plus b times a minus b. So here a is x, b is 2, right? So a squared is just x squared, so this is 4, right? So this is x plus 2 and then x minus 2. So this is a general formula, and we can use this general formula to factor this term. And so by looking at this equation, we can easily see that there are 3 roots to this higher degree equation, right? Because this is a times b times c, and this equals to 0. So the 3 roots are a equals to 1, or a equals to 0, or b equals to 0, or 3 equals to 0, right? It's really easy. And so when a equals to 0, the x is 1. So when b equals to 0, x is minus 2. When c equals to 0, x is 2. So 1 minus 2 and 2 are the 3 roots to this equation. Okay, but sometimes it's not that easy to factor the function like this, right? So this is an easy example because we can just factor the function by just looking at it. But sometimes it's hard to find a solution in this way. So I'll talk about the general way later on, but first we have two notes here. So first note, generally an nth degree polynomial equation should yield a total of n roots. So here, this is a third degree polynomial function because the highest degree of x is 3, right? So because the third degree polynomial function, so there should be a total of 3 roots. So that's why you have x1, x2, and x3, 3 roots here. And second note, each root must be a divisor of the constant term. So in this example, the constant term is 4, right? So this note means that each root 1 minus 2 or 2 should be a divisor of the 4, the constant term, right? The reason is that after we expand this function, right? After we expand this function, we can see that all the other term has x, right? So the only way that you can yield the constant here is to multiply all the constants here, right? Only if you multiply all the constants here can you yield the constant term of 4. But in other ways, there should be an x because all the other 3 terms here contain an x. Right? And that is because you multiply this constant term with an x in the other term. Well, how can we obtain this 4? Is to multiply only the constant terms, the 3 constant terms, have a yield of 4 here. So that's why each of the root has to be a divisor of the constant term, such that when you multiply all of them together, each root together, you yield the constant term here, right? Okay. So here we have 3 roots, and then we have 3 theorems here. Theorem 1, we have already talked about that. Given the polynomial equation x to the n plus a n minus 1 times x n minus 1 plus until a1x plus a0 equals to 0. Right? Given this kind of polynomial equation, where all the coefficients are integers, so that means that all the a's here, this is called coefficients. So all the a's here are integers, right? And the coefficient of of x to the n is 1. So here we have 1 times x to the n. And if there exist integer roots, then each of them must be a divisor of a0. Right? So this is just so this example is just a example of the theorem 1 here, right? We'll already talk about that. So here the coefficient of the highest degree of x is 1, and then the constant term is 4. And we have 3 integer roots, and all of them should be a divisor of 4, right? But pay attention that for the divisors, you don't have to be strictly positive. Right? For example, minus 2 is also the divisor of 4, although it is negative, but it doesn't matter when we are thinking about divisors. Right? Both the positive 2 and negative 2 are considered to be divisors of 4. So the signs are not important here. And the second theorem, given the polynomial equation with integer coefficients, that means that all the a's here are integers, right? And we have this form. So the difference between this equation and this equation is that here, this is a more general case because the coefficient of x to the n is an. It doesn't necessarily have to be 1. So that's the difference between the 2 equations. So theorem 2 is more general. And if there exists a rational root, R over S. As we said that the rational numbers, they're called rational numbers because they can be represented by a ratio of two integers. Right, this is in chapter 2. So R and S are both integers, but they are without a common divisor except 1. So that means that if R is 10 and S is 5, then this doesn't hold because they have a common divisor 5 and 1, right? Not only 1, but they have another divisor called 5. So R and S, they have other divisors, so they doesn't hold for this case. But if R is 5, S is 2, then this holds, right? This meets the condition because the only divisor is 1 for both of them. Right? So this is what it means by saying the rational root. Then R is a divisor of A0 and S is a divisor of AN. So let's look at an example here. So this is a complicated equation, right? So this is a 4th degree polynomial equation. So it means that we have 4 roots, right? So if there is some rational root, then we want to find them out. The way we do this is to first write out what is A0 and what is AN. So here in the example, A0 is 12, just a constant term, and AN is 2, right? AN is a coefficient of the highest degree x. And so if there's a rational root, so R should be a divisor of A0. In this case, this is a divisor of 12. Divisor of 12. So we have a lot of divisors of 12. They are 1 minus 1, 2 minus 2, 3 minus 3, and all the others until 12 and minus 12. Right? So we have a lot of potential pool for R to choose. And for S, the fewer, because S is a divisor of 2. Right? The divisor of 2 has only 4 terms, 4 numbers, 1 minus 1, 2, and minus 2. So here we have the potential pool for R and S to choose. Okay. So if there's a rational root, then R and S should be chosen from these 2 sets, respectively. And so for the R over S, what we're going to do is to combine each one of them, calculate each one of this, and find out how many distinct solutions that we can find for R over S. So that takes a lot of time, but because we have to combine each R with each S, and then we find that, okay, how many solutions we can find. So for example, if R is 1, then R divided by 1 is 1, R over minus 1 is minus 1, R divided by 2 is 1/2, 1 divided by minus 2 is minus 1/2. So we're done with R equals to 1. And then we switch to R equals to minus 1. And then we complete by using all the R's in the potential pool here, right? And then we find out, okay, using all the pools here, R over S should be within this set. There are a lot of numbers to choose, right? So we know that if there's a rational root, then this root has to be within this set. And then what we're gonna do, okay, it takes a lot of time. What you're gonna do next is to verify R over S one by one, right? One by one. So that means that, okay, first we choose the root to be 1, and then we plug in x equals to 1, into this equation. And we find out if this holds. Right? So for example, x equals to 1, plug in. So this is 2 plus 5 minus 11 minus 20 plus 12. But this is not 0. Right? So 1 is not a root. So we cancel that out. And then we move to minus 1, plug in x equals to minus 1 to this equation and find out, okay, this equation still doesn't hold. So minus 1 is still not a root, right? But if we plug in 1/2, we find out, okay, after plugging 1/2, this equation holds. So that means that 1/2 is one of the rational root for this equation. And then we plug in 1 by 1, and then we can find all the roots after cancel out. And we can find that, okay, there are exactly 4 roots, 4 rational roots for this equation. Right, so what we're going to do is we have to first find out all the r, all the s, and all the r over s, and then we plug in all the r over s to this equation, and then finally we can find how many roots are exactly there that we can find. Right, in this example, there are 4 roots. And so by factorization, we can know that the equation can be rewritten to this. So there are 4 roots here. So this is a more general way that we can solve for the roots of the higher order degree polynomial function. So if you expand this final equation after factorization, if you expand this and get rid of these parameters, you can find that this equation is exactly this one, right? They're the same. But here we write this equation in the root form, right? Multiplying all the roots. Okay. So this is a theorem 2. And theorem 3 is much easier to understand, given the same polynomial equation, that is, if the summation of all the coefficients are 0. So all the coefficients are from a0 to an, right? If we summarize, or if we add all of them together, then the summation should be 0, right? So if this is the case, then x equals to 1 is a root of the equation. So that means that, for example, for this equation, right? So all the coefficients are 1, 1, minus 1, and minus 1. And we sum everything out, and then this should be 0, right? 1 plus 1 plus minus 1 plus minus 1. So this should be 0. And so x is 1. X equals to 1 is one of the roots. Right, okay. So if you plug in x equals to 1, this is 1 plus 1 minus 1 minus 1. So this is 0. Okay, so there's theorem 3. But more generally, we use theorem 2 to find the solution. So if you see a polynomial equation that looks like the theorem 1 here, I mean the coefficient of the highest degree of x is 1, then if you want to find the integer root, if there's only integer root, then you can use the theorem 1 to find the solution. But theorem 2 is more general, right? It's more general. That you can find all the rational root, including the integer root, using the theorem 2. So let's look at an example for the theorem 1 here. Another example. We have this equation. So from this equation, so we know that, okay, there are 3 roots, right? Because it's a third degree polynomial function. And the highest degree of x cubed, highest degree of x is x cubed, and the coefficient is 1. So we can first use the theorem 1 to find if there's any integer roots. right? So A0 is 10, and we know that if there's an integer root, then all the roots have to be the divisor of the constant term, right? A0, the constant term. So first we need to find out all the divisors of 10. So we have 8 of them, right, including the positive and negative ones, right? All of them are 8 of them. So again, what we're going to do is to plug in one by one into this equation to see that if this equation holds, to plug in all the numbers. And we find out, okay, there are exactly 3 roots here, 1, minus 2, and 5. So we don't have to use the theorem 2 to find all the other rational roots, like 1/2, 1/3, something like this, right? All the 3 roots are integers. So in this example, it's very easy to find all the roots by simply plugging all the factors here. So we can rewrite this complicated polynomial function into a simpler one after factorization, right? And if you expand this equation, get rid of these parentheses, you can find that these two are equal, right? And we write this equation into the root form, right? So the root 1 is 1, root 2 is 5, root 3 is minus 2. Right? So this is called factorization. But more generally, we use the theorem 2 to solve the equation because theorem 2, the form of the function is more general. The coefficient here is an, is not necessarily 1. And the root here is a rational root. It includes all the fractions, right? 1/2, 1/3, all the fractions, and all the integers, right? And we only talk about the rational root here, but we don't talk about the, for example, the complex numbers here, right? So I think all the roots in this course should be the rational root, and so you don't have to worry about the other kind of complex numbers or complex roots here. So theorem 2 is more general, and theorem 1 only applies when the coefficient here is 1, and only applies for the integer roots. Right? If there's no integer root, then you cannot find the solution using theorem 1. Right? But since most of the roots are rational roots, or actually all of the roots in this course should be rational roots, so you can use theorem 2 to find all the roots for the equation. Although it's a little bit time consuming and complicated, you have to do a lot of simple calculation and find out all the pools here is very easy to miss something, right? Miss some of the roots here. But if you plug in one by one, then finally you can find all the roots here, right? So it's a more general way that we use to solve for the higher degree polynomial function.